Chapter 19, Part 2, Cardiac Physiology. This screencast is going to focus on generation of action potentials in contractile muscle, not nodal cells as was addressed in the previous screencast. Here, we're basically looking at a cardiac muscle cell at rest, and a couple of things that I want to point out here. Take note of the very negative resting membrane potential of negative 90 millivolts. This is a true resting membrane potential, and we will see why in just a little bit. But this is much more negative than a neuron, so it's much more hyperpolarized. So think about this. This is something that's going to take longer to get to threshold. Therefore, we're looking at some additional time for ventricular filling. The next thing that we have to look at are what are the channels that we find within cardiac muscle cell, indicating the ions that play a role in the generation of action potentials in contractile cells. So first, we're going to have fast voltage-gated sodium channels. We're going to have fast voltage-gated potassium channels. And we're going to have slow voltage-gated calcium channels. So similar to some channels that we have seen previously, but let's actually take a look at how these action potentials are generated. Now, note, depolarization is similar to what we saw in our frame of reference, which was a neuron. So here we're basically looking at the rapid inflow of sodium through these fast voltage-gated sodium channels, and this is resulting in a very major rapid depolarization and going from negative 90 to about plus 30 millivolts. So this is a very significant change in membrane potential. Then we have something very different than we saw within the pacing cells. We have what we refer to here as a plateau. Now, if we look at what's happening here, there are actually two voltage-gated channels coming in. We have a potassium channel open and a calcium channel open. So we're having calcium come into the cell, yet potassium is leaving, and this is happening simultaneously. So this is really going to interfere with returning to resting membrane potential. It is slowing things down, and you can see that the time of a cardiac action potential is long, and the width is increased due to the plateau. Then we're actually going to get to depolarization, and now this is usual. We're actually going to look at potassium channels are the only channels that are open. Potassium will be leaving the cell, and this is going to bring us back to negative 90 millivolts. But also note here, we spend time at this negative 90. This is why I like to call this a true resting membrane potential and not a false resting membrane potential, which was the term we used when we're talking about pacing cells. Now, I want to spend some time with this particular figure because I think it is important. And so the first one that we're looking at are what's happening during depolarization. So note that the only channel that's open at this point in time are fast voltage-gated sodium channels. This results in depolarization as sodium is rushing through these channels, and we see basically a change in resting membrane potential from negative 90 millivolts to plus 30. Then we are going to see these sodium channels close. The next phase is the plateau phase. Take a note here. Now, the sodium voltage-gated channels are closed, but the remaining two channels, the slow voltage-gated calcium channels and the voltage-gated potassium channels, are both open at the same time. So we have plus 2 calcium coming into the cell, plus 1 potassium leaving, and so really this is maintaining a state of depolarization. Then we get to the last phase, which is repolarization. So the only channels open at this point in time are the voltage-gated potassium channels. This results in the only ion moving is potassium out of the cell, and this is going to return us to resting membrane potential of negative 90 millivolts. Now, what we have to keep in mind here is what is being initiated by this electrical process and these action potentials. Remember, electrical first, mechanical second. So because of these electrical events, we are now going to see cross-bridge cycling, just like what happened when you saw force being produced in skeletal muscle. calcium enters the sarcoplasm from both the interstitial fluid and the sarcoplasmic reticulum. This is very different. When we saw skeletal muscle, the only source of calcium was the sarcoplasmic reticulum. In cardiac muscle, it's coming from not only the sarcoplasmic reticulum, but also the interstitial fluid. As usual, this calcium will bind to troponin, and it's going to be responsible for the initiation of cross-bridge cycling. Here we have the formation of cross bridges, the power stroke, release of the myosin head, reset of myosin head, and so on as long as calcium is available. Once calcium levels start to decrease, this results in relaxation. The channels will close, and pumps will move it not just back into the sarcoplasmic reticulum, but also out of the cell and back into the interstitial fluid. Now, what's very critical and a big difference between cardiac muscle and skeletal muscle is cardiac muscle cannot exhibit tetany. Unlike skeletal muscle, cardiac cells have a long refractory period. What this means that these cells cannot fire another impulse during the refractory period. When we look at how long the refractory period in a cardiac muscle cell, the plateau phase, is about 250 milliseconds. The heart cell contracts and relaxes before it can be stimulated again. This refractory period makes it impossible for a tetanic contraction to take place. And when we talk about cardiac muscle, this is critical to its function because remember, it's pulsatile. I contract, I relax, I contract. Unlike skeletal muscle, where we need to maintain a sustained force. Now, this is something similar to what you saw previously in 144 when you're talking about the lack of a refractory period with respect to skeletal muscle. So here we're looking at a single twitch, and so we have excitation, contraction, coupling. So there's my excitation, the depolarization, and then we actually have the force generated here as far as muscle contraction. Now, here we're looking at this very familiar diagram that you probably saw in 144, but I want to take some time here because one of the things that's not often explained about this diagram is that the data in this figure was actually not collected in an intact animal. So what happened here was a muscle fiber is extracted and it's going to be stimulated externally. That is the only way you can actually control the rate of stimulation. In an intact skeletal muscle, the firing rate is going to be based on the motor neuron. But it's very difficult to see this. So here we see the fact that as you increase the frequency of stimulation, you actually see an increase in muscle tension or force. You get to incomplete tetany, and eventually you get to tetany. And note what tetany is. It is a constant contractile force. And this is critical because this is how skeletal muscle works. You basically have a consistent amount of force being produced. So kind of imagine if you were a server trying to deliver drinks to a table. There's no way that that would be possible unless skeletal muscle exhibited tetany, this sustained forceful contraction of a particular amount of force. Now, that is not desirable when we look at cardiac muscle. So here, if we look at depolarization, so there's that action potential, and notice that there's going to be this period of time during this refractory period in which no other action potential can be generated. This basically means that there's no tetanic contraction. So we're only going to get this frequent stimulation when one is done, then we have the other. So this is a very critical concept here when we look at these refractory periods, because in cardiac muscle, they exist, and what they are preventing from happening is tetanic contraction.